Okay, so in last lecture, recorded lecture, I have sent you the lecture of video of recorded video of design of circular water tank with flexible base. Okay, now we'll be starting with the design of water tank with fixed base and it is resting on ground. Okay, we have to do this design as per IS code method. Okay, we know that there are certain IS codes are there. I have already told you in the that recorded lecture. Okay, so we have four of these IS codes. Just a minute. Okay, the first one is IS 3370/2009. Okay, this is a revised version. Earlier version is now overwritten by this particular version of IS code. Okay, the second one is IS 3370/2009. Okay, this is part 2. First one was part 1. Then we have IS 3370/1967 part 3. Okay, the first one is guidelines for general requirements of water tank. Okay, it gives first IS code gives the guidelines for general requirements of water tanks or liquid retaining structures. Okay, then we have IS 3370 part 2 code of practice for concrete structure for storage of liquids or reinforced concrete structures. Okay, then we have IS 3370/1967 part 3. Okay, this is for pre-stressed concrete structure. Okay, it is for design of pre-stressed concrete structure. And then we have IS 3370/1967 part 4 code of practice for concrete structures for storage of liquids design tables. Okay, so these two gives general guidelines, whereas it can also be used for design of flexible water tanks by using approximate method, whereas if you want to design as per IS code method, then you will be required to use this IS 3370 part 4 IS code. Okay, this particular IS code gives some design tables based on some experience gained by the designers. Okay, based on that some design tables are developed and based on that we have to design the IS your water tank. Okay, so I'll explain some portion. Okay, now these are some general requirements of design of water tanks. Okay, the first is that the concrete mix whichever used, that should be at least M30. Okay, because if we are using higher grade of concrete, it will result in less cracking in your concrete structure. Okay, as we are designing our water tank for retaining water, therefore cracking is not permitted, or the width of cracking in your concrete that should not exceed the permissible limit. Okay, therefore higher grade of concrete and thus M30 grade of concrete should be used. Whereas at the same time we know there are some exposure conditions given in IS 456/2000. So whenever we will be designing a water tank, we will be considering that the water tank structure is subjected to severe exposure condition. Okay, based on that we have to take the minimum grade of concrete, minimum cover requirement, minimum or maximum cement content. Okay, then the maximum cement content, this should not exceed 400 kg per cubic meter. Okay, why this limit is there? Because if we are using more cement in your concrete, then what will happen? More heat of hydration will be developed and this will result in more cracking or increase in the width of crackings. Okay, whereas then the width of cracking can be controlled by using plasticizers. The width of cracking can be used controlled by using the plasticizer, whereas minimum cement content for water retaining or liquid retaining structure, this should be 320 kg per cubic meter. 320 kg per cubic meter. Okay, okay, then the cracking can also be reduced by using steep changes in the temperature and moisture content. Therefore, what we have to do, we have to cure that concrete which is used for water retaining structure for at least 14 days, for at least 14 days. At the same time, correct placement of steel reinforcement, use of deform bar instead of your mild steel bars, and at the same time bars which are closely spaced, that should be used to reduce the cracking, because if there are cracks are present in your water retaining structure, it will be subjected to risk of leakage. Okay. Then the maximum calculated surface width of the crack for direct tension and flexure, this should not be more than 0.2 mm, 0.2 mm. Okay, with specified cover. So how we will be getting this 0.2 mm width limit? What we will be doing, we will limit the stresses which are developed. Okay, we will limit the stresses which are developed in your concrete, so that the maximum width of your concrete cracking, this should be 0.2 mm, this should be 0.2 mm. Okay. So there are two methods of design of water tanks. The first one is limit state method and the second one is working stress method. Okay. Now working stress method, you know working stress method, what will be considering that there are some assumptions. The first assumption is plane section remains plane before bending and after bending. Then the steel and concrete behave elastically and modular ratio M is given by this particular formula. This is covered in your RCC. This particular formula is covered in your RCC part. Okay. Then the tensile stresses in concrete are limited to some values given in table 22. Okay. So there are some values given in IS 3370. Okay, I think that's table number 1. Okay, that is table number 1 given in IS 3370 2009 part 2. Okay, where depending upon the grade of concrete, we are given with some tension, direct tension values and flexural tension permitted values. Okay, so this is the table which we will be using for design purpose. Then the permissible stresses in your concrete from strength calculation point of view. Okay, this is the table which is given in IS 3370 2009 at page number 3. Okay, from we are given some values of grade of concrete. Based on that grade of concrete, some values of sigma CBC, sigma CC and tau BD, that is average bond stress. These values are given. Okay, I think you are more familiar with this sigma CBC. This is permissible compressive this is permissible compressive stress in concrete in bending. Okay, whereas this sigma CC, okay, this sigma CC, this is the value of compressive stresses in concrete in direct stress. Okay, whereas tau BD, this is the bond stresses in the concrete. Okay, so these all these terms are already covered in your RCC. Okay, RCC 1. Okay, resistance to there. Then we have this particular table, table number 3. Okay, this is also given in IS 3370 part 2 2009 version. Okay, at page number 3. Okay, what it gives, it gives the values of tensile stresses in your steel. Okay, so we need HYSD steel only. So if we are having, if we are considering this value of stresses in the steel for direct tension, bendings and shear, we have to use this 130 Newton per mm square, whereas if we are considering for compressive stresses in columns subjected to direct load, we have to use this value of 140 Newton per mm square. We won't be using these two values because these are for plain mild steel bars. Okay. Okay, now some IS code recommendations are there based upon which we have to provide the steel. Okay, the first recommendation, these are given in IS 3370 part 2. Okay, these are given in IS 3370 part 2. Okay, the minimum reinforcement in walls, floors and roof. Okay. Okay, first I have to explain you some part. Okay. So there are basically three parts of any water tanks are there. Okay, actually I covered this particular portion in the first lecture, but as you have not gone through that particular lecture, I'll explain this in short only. Okay, there are three parts of any water tanks are there. The first one is, okay, the first one is your base slab or base. Okay, then we have some walls, okay, walls of water tank, and then we have cover. Okay, then we have cover. If you see in plan, this will be something like this. Okay, this will be wall. Okay, this will be your wall. Okay, this is in plan and this is in elevation. Okay, so these three parts are there. We are having cover, which will be used for covering the to prevent fall of any debris or any other material which are not required to be stored in the water. Then we have these walls. Okay, this will help for the storage of water. This will help for storage of water, and this is the base slab. It will provide the base for your water tank or foundation for your water tank. Okay, what we will be doing, we will not fill the water tank completely. What we will be doing, we will provide some freeboard. We will provide some freeboard. Okay, freeboard means up to certain depth we will be filling the water. Let us consider up to this depth, and this much height is kept as a freeboard. This is kept as a freeboard, so that when if there are chances of overtopping of water from the water tank, then this should be this portion should be used. Okay, at the same time, while designing any water tank wall, what we will be doing, we will be designing this complete wall. Okay, including this freeboard for design purpose. Okay. So there are some general requirements of detailing of water tanks are there. Why these general requirements are given? Because providing some extra amount of steel will reduce the development of cracks in your water retaining structure. Okay, so the first recommendation is the minimum reinforcement in walls, floors and roof in each two direction at right angles within each surface zone. Okay, within each surface zone. This word is more important. This should not be less than 0.35% of the cross section of surface zone for HYSD steel bar. Okay, so minimum steel required to be provided is 0.35% of the cross sectional area. 0.35% of the cross sectional area. Okay, so cross sectional area of surface zone. Okay, this term is very important in this case. Now, what is your surface zone? So what we will be doing, whenever we will be designing some floor or wall or roof of a water tank, we will consider if the depth of your that particular member or thickness of that particular member is less than 500 mm, then what we will be doing, if we are providing some steel reinforcement in the top, okay, this steel, for calculation of this steel reinforcement in the top, what we will be doing, we will be considering half of the depth, that is d by 2, and for remaining steel which is provided at the bottom, what we will be doing, we will be again considering d by 2. So if we have 300 mm depth, then calculation of AST minimum we will be considering for top reinforcement, we will be considering 150 mm. Okay, so AST will be 0.35 divided by 0.35 into 150 multiplied by 1000 divided by 100. So this much steel is required to be provided. If 0.3 meter thickness of member is there, then this top reinforcement will be provided with this amount, whereas this bottom reinforcement will be again provided with this amount only, that is 0.35 into 150 into 1000. Sorry, this should be 1000. This is width. Okay, so minimum steel is this much, whereas if the depth of your member this is more than 500 mm, this is more than 500 mm. Then for top steel, what we'll be doing, we'll be considering only this much portion. This is called as surface zone. This portion is considered as a surface zone, and AST here it will be AST provided will be 0.35 divided by 100 multiplied by this 250, multiplied by this 250 figure, that is 250 mm, 250 multiplied by 1000. So this will be the AST minimum which will be provided in the top, and similar amount of AST, that is 0.35 divided by 100 into 250 multiplied by 1000. This much amount of AST will be provided in the bottom face for these particular members, that is for wall, floors and roofs. Okay. Then the minimum reinforcement that can be that can further reduce to 0.24% for deformed bars, and for plain bars for tanks not having any dimension more than 15 meters, we can also reduce this AST minimum up to 0.34. but for safety, what we'll be doing, we'll be using this particular value which was given in the previous recommendation, that is 0.35%. okay. Which is indicated here. We'll be using this particular value of 0.35% only. Okay. Then in tanks and slabs having thickness less than 200 mm, the reinforcement can be placed on one face only. So if we are having thickness, this thickness is less than, consider this is your wall, this is your base of your, okay, this is your wall of water tank, okay, and this is the base, this is your base. If thickness of this particular member, this thickness is less than 200 mm, if it is less than 200 mm, then steel reinforcement can be provided on one face like this. Okay. Then steel reinforcement can be provided on one face like this. Okay, and here at the bottom. Okay, so like this we can provide the steel reinforcement. Then for ground slab or base slab having thickness less than 300 mm, again same point is given, that is reinforcement can be provided on the only one face. Okay. Now the spacing of steel reinforcement, should not exceed 300 mm or the thickness of section, whichever is less. So spacing of reinforcement, this should not be more than 300 mm or the thickness of your member. Okay. At the same time, the size of bar, distance between the bars, lap, bend, then development length, all these values should be taken as per IS 456-2000. Okay. So for remaining portion, IS 456-2000 is applicable. Okay. Now some IS code recommendation regarding the calculation of AST minimum when we will be providing steel. These are given in this particular figure. Okay, same thing is given, that is 0.35% steel is required to be provided. Minimum AST should be 0.35%. Okay, that is given in this particular figures. Okay, this is given based on the thickness of your members. Now we are having some different types of water tanks are there. Okay, I have to go back again because you have not gone through that video. Okay, we are having some different types of water tanks are there. Okay, based on the base condition. The first type of water tank is a water tank with flexible base. Okay, so in this type of water tank, let us consider we are having our base slab like this. Okay, we are having our base slab like this. Okay, like this we will be having our base slab. Okay, so this is one of the wall and this is our another wall. Let us consider like this. So what we will be doing in case of water tanks with flexible base will be providing some rubber pad here below the wall, rubber pad here below the wall like this. We will be providing some rubber pad like this here below the wall. Okay, we will be providing some rubber pad like arrangement here below the wall. Okay, and what again we will be doing, we will provide some sealing material here. Okay, here you can see here written sealing compound. Okay, so some sealing material is provided between the joint between your wall and base, and a rubber pad is provided below the water tank. Okay, you can see here some rubber pad is provided. Okay, so what does this serves? Okay, whenever some water pressure will be developed like this, okay, water pressure will be developed like this, what will happen? This wall, this particular wall will tend to move in this direction slightly. Okay, as it is not fixed with the base, here, because it is resting on some rubber pad. Okay, this rubber pad and this particular sealant material will prevent the leakage of water from this particular water tank. Okay, and as it is not fixed with the base, what will happen? Whenever there will be some water pressure will be developed from inside the water tank, this particular wall, this will move in this particular direction by small amount. This will move in left direction by small amount, and this particular wall will be moving away from the water. Okay, due to provision of this particular rubber pad which is provided at the bottom of your water tank. I don't think any of you have seen this type of water tank, because this type of water tanks are constructed very rarely. Even I haven't also seen such type of water tanks. Okay, so the purpose is that why we are providing this rubber pad below the wall, because if we are providing rubber pad below the wall, what will happen? There will be no bending moments will be developed. No bending moment will be developed in the wall. Okay, because it is not fixed here, it is not fixed with the base, therefore no bending moments are developed in the wall, and only hoop tension. You know what is hoop tension? If some circular water tank is there, what will happen? The water pressure will be acting in all the direction on the walls of your water tank like this. Okay, this let us consider this is your elevation, so pressure will be acting like this in all the directions. So due to this, some hoop tension is developed. Okay, if you consider small element of this water tank, some hoop tension will be developed like this, and it will not cause any bending moment. Okay, so if we don't want any bending moment to be developed in your water tank wall, then we will be using this type of water tank with flexible base. Okay, these are very rarely constructed, and I haven't seen any of the water tank which are constructed using this particular technique of flexible base. Then we have second type of water tank, that is water tank with hinged base. So again, what we'll be doing, we'll be providing some rubber pad below here like this, some rubber pad below the wall. Okay, again some sealing material will be provided between the joint between your water tank and wall, but at the same time what we'll be doing, will be extending the steel reinforcement, will be extending the steel reinforcement of the wall, inside the base of your, this is the base of your water tank, and this steel reinforcement will be extended in the base of your water tank. Okay, therefore some hinge type arrangement is developed. So this type of water tank is considered as water tank resting on ground with hinged base. Okay, then we have third type of water tank, it is called as water tank with fixed base. Okay, now in case of water tank with fixed base, this is the wall. Okay, in case of water tank with fixed base, we have a wall like this here. Okay, we have wall like this here. Okay, and then we have base slab here. Okay, this is your base slab, we have wall here. So what we'll be doing, we'll be casting these two members, that is wall and your base slab, monolithically, means at the same time we'll be casting these two members, wall and your base slab. At the same time, what we'll be doing, we'll be extending the steel reinforcement of wall, will be extending the steel reinforcement of the wall into the base of your water tank. At the same time, some arrangement like this is also provided, so that complete fixity is developed. Complete fixity is developed between the wall and the base slab. So this type of water tank is considered as water tank with fixed base. Water tank with fixed base. Okay, generally what we will be doing, okay, complete fixity between the wall and base slab is practically not possible. It is practically not possible. So whenever we will be designing your water tank, what we will be doing, we will be designing some we will be considering some hinge here. Okay, this will result in some better arrangement of better approach. Okay, so these three types of water tanks are there based on the floor base condition. Okay, the first one is flexible base, hinged base and fixed base. Okay, so we'll be designing these two types of water tanks, that is water tank with fixed base. We'll be designing this particular water tank by approximate method. Okay, by approximate method, whereas water tank with fixed base will be designing this particular type of water tank by using IS code method. Okay, okay, these three tables I have explained earlier. Okay, these will be used for calculating the stresses developed in your steel and concrete. Or calculating means finding the values of maximum permissible stresses in steel and concrete. Okay, this will be used for steel. These are some general recommendations which we have already discussed. Okay, we have to keep in mind that minimum steel reinforcement that is required to be provided, that shall be minimum 0.35% of the cross sectional area of your steel, cross sectional area of your member. Okay, this is some enlarged view of water tank with flexible base. You can see here some rubber pad arrangement is provided. You can see rubber pad is provided here. One sealant is again provided here, and for joint sealing you can see here, for joint sealing some material is provided here. Okay, these are very rare type of water tank. You can see in enlarged view rubber pad is provided like this. This pink color is rubber pad. This pink color portion, this is your rubber pad over which your water tank wall will be sliding slightly. Okay, then we have some sealant material here. You can see which is shown by this yellow color here, sealant material. Okay, some PVC water stopper will be provided. Some PVC water stopper will be provided. You can see here. Okay, just a minute, change the color. Okay, some water stopper arrangement is provided. It will prevent the leakage of water. Okay, and water depth is up to this particular level. This particular portion, this is called as freeboard. This is called as freeboard. Okay, and the steel will be provided as shown in this particular figure. Okay, this is for water tank with flexible base. Okay, I have already covered the water tank with flexible base in another video. You go through that particular video. Okay. Now hoop tension whichever developed, it is given by this particular formula. Okay, just keep in mind this hoop tension T value is given by this particular formula, gamma H into D by 2, where this T is hoop tension, H is the height of water in your water tank, D is the diameter of water tank, and gamma is the unit weight of water. We consider that as either 10 kg per cubic meter, kilonewton per cubic meter, or 9.81 kilonewton per cubic meter. Okay, so just keep in mind this particular formula. This is hoop tension T is equal to gamma H into D by 2, or this can be also written as gamma H into R, where R is the radius of your water tank. Okay, better we consider in terms of D. Okay, the same thing is explained here. This formula is given, that is hoop tension is equal to gamma H into D by 2. Okay, this is how the hoop tension will be developed in your water tank. This is the plan of water tank. Okay, I will be covering in a hurry because I have to cover the design of water tank with fixed base. Okay, just for giving you the idea how we will be designing, because I have already covered this portion in the recorded video which I have sent you on the YouTube. Okay, this is related with your flexible water tank. Okay, yeah. Minimum freeboard of 200 mm is required to be provided for design of water tank. Okay, this will prevent whenever there will be some more capacity, sorry, the water tank is filled up to the top. Okay, this can be used as a freeboard. Okay, okay, these are some terms which are which will be coming into contact while designing this type of water tanks. The first one is sigma ct, that is permissible direct tensile stress in concrete. Sigma bt is the permissible tensile stress due to bending, okay, in concrete. Sigma cbc is the permissible stress in concrete due to bending, whereas sigma st is the permissible stresses in the steel. All these terms are already covered in your rcc. All these terms are already covered in your rcc. Okay, now next portion is regarding design of water tank with flexible base. You go through this particular problem. I have uploaded this on YouTube. Okay, this is designed for water tank with flexible base, and today I will be covering the design of water tank with fixed base only. Okay, so these points I already explained, which are different types of water tanks based on the floor base condition, and we'll be designing this water tank with fixed base. Okay, this is generally constructed design of water tank with fixed base. Even design of design of water tank with flexible base is rare. This is rare case. Now in case of, okay, we'll start here, design of water tank with fixed base. Now in case of design of water tanks with fixed base, what we'll be doing, we'll be casting this particular wall and this base slab. Okay, this base slab monolithically, means the steel of this particular two members will be extending in each other at the same time. They will be casted at the same time. Okay, so this will bring some fixity at the base of your water tank. Okay, now you can see, if our water tank is like this, let us consider this is the water tank wall. Let us consider this is the let us consider we have our water tank wall like this. Okay, we have our water tank, we have our water tank walls like this. These are wall. Okay, and this is your base slab. This is your base slab. Okay, now we are providing fixed arrangement here between the bond between here. This is fixed. Okay, this is fixed, and we know that there will be some water pressure which will be acting on the wall. There will be some water pressure will be there which will be acting on the wall. Let us consider the left side of your wall. Okay, let us consider water pressure is acting like this. The water is filled up to the top, and the water pressure is acting like this over this particular wall. Okay, over this particular wall some water pressure is acting. What will happen? This water pressure, okay, this will create different types of forces. The first type of force which is developed, this will be the bending moment. Why bending moment? Because the wall is fixed with the base. This particular wall, this is fixed with this particular base slab. Therefore, due to this particular water pressure having maximum value here, this value will be gamma into h, where h is the height of your water tank. This height of your water tank, then the pressure intensity at the maximum pressure intensity will be gamma into h. Okay, the maximum pressure intensity will be gamma into h. Okay, so due to this gamma into h, some bending moments will be developed at the same time. Okay, as this water tank is a circular water tank, this is your circular water tank, and the water pressure is acting in all the direction over the wall like this. Water pressure is acting over the wall in all the direction. Therefore, hoop tension will also be developed. Hoop tension will also be developed. Okay, now what will be the amount of this hoop tension and bending moment, that we have to fix, and at up to what height these two will be acting. Okay, so as the movement of this wall, is restrained, you can see here. Okay, you can see here, as we are providing some fixity here. Let us consider we are providing fixity here for the wall, and the wall is subjected to some lateral pressure from the water, okay, like this. Okay, water pressure will be acting over this particular wall. The intensity here, it will be gamma into h. The intensity here, it will be gamma into h. Okay, due to this, two types of forces are developing. The first one is bending moment, and the second one is your hoop tension. Now this particular bending moment, okay, this particular bending moment will develop some cantilever action in your water tank wall, because it is fixed. The water tank wall is fixed at the base, whereas it is free at the top. Here. Okay, therefore what will happen, due to this water pressure, okay, force will be acting like this here, and this will cause bending of this particular wall like this. Okay, this will be the due to bending moment. At the same time, what will happen, due to hoop tension acting on this particular wall, this will again bend. Okay, this will again bend like this. Okay, so we have to use the combination of your bending moment, and hoop tension while designing your water tank with fixed base. Now just a minute. Now as per our experience or previous experience while designing of any water tank, it is considered that if this is your water pressure which is acting on the water, if this is the water pressure which is acting on the water tank wall, okay, this intensity will be gamma into h. Okay, so this water pressure is acting, so it is considered that the cantilever action, okay, due to the water pressure, this is predominant, or this is mainly affecting the design of structure up to a height of h by 3, or 1 meter, whichever is greater. So this cantilever action which is developed due to the water pressure, this is more predominant up to a height of h by 3. This cantilever action which is developed due to this water pressure is more predominant up to a height of h by 3 from the base. Okay, so you can see here up to a height of h by 3 from base, or 1 meter, will be designing the water tank for the bending moment from bending moment criteria, whereas remaining of the portion, that is this particular portion above h by 3, okay, above this is greater than h by 3, so above h by 3, this will be more predominantly affected by your hoop tension. So while designing first portion, that is up to a height of h by 3 or 1 meter, will be designing considering the bending moment criteria, whereas for remaining portion will be considering the hoop tension criteria for design. Okay, you can see the behavior, combined behavior here. Okay, so up to a height of h by 3 from the base, up to a height of h by 3 or 1 meter, whichever is more, the action which is more predominant, that is cantilever action. For remaining portion, hoop tension will be more predominant, due to the action of this particular water pressure, These two types of forces will be developed. The first one is hoop tension, and the second one is the bending moment, which will be causing the cantilever action in your water tank wall. Okay, now how the distribution of these two, that is hoop tension and your cantilever behavior, that is separated. Now if you can see here, some water tank wall is shown, and this type of water pressure is acting on this particular water tank wall. This type of water pressure, this is acting on this water tank wall. The maximum intensity of water pressure, this will be gamma into h. This will be gamma into h at the base. Now up to a height of h by 3, as we have discussed earlier, up to a height of h by 3 or 1 meter, whichever is more, up to this height we will be considering the cantilever action is more predominant. So this particular area of triangle OBC, you can see here triangle OBC, this particular triangle, okay, this will develop the bending moment, or cantilever action, okay. So the area of this particular triangular portion, this will be developing the cantilever action, whereas if you see this particular portion, that is this triangle ABO, which is shown by crosses, okay, this particular triangle, or this is shown by this blue color, okay, the water pressure due to this particular triangular portion, this will cause hoop tension, in your wall, whereas this pink portion of your pressure diagram, this will cause the bending moment or cantilever action, So one thing we have to keep in mind, this bending moment is more predominant up to a height of h by 3 or 1 meter from the base, whereas for remaining portion, this hoop tension is more predominant, having the maximum value at this point B. We can calculate these values by using similarity of triangles, okay. You can see here we have small h denoting the height up to which cantilever action is more predominant, and for remaining height of capital H minus small h, the hoop tension action will be more predominant, okay. Now for design of water tank by using IS code method, we have some IS code is given, that is IS 3370 part 4, which gives some tables for design tables, okay. IS 3370 is there, which gives some design tables. Okay, just a minute. So this is your IS 3370. The title of IS code is Code of Practice for Concrete Structures, okay, for the storage of liquids, part 4, design tables. So as title indicates, it gives some design tables for design of water retaining structures, okay. This version is 1967 and it was reaffirmed in 2008, okay. So we'll directly go to the design tables, okay. This part is already explained. Table 1. Initial tables are not that much important for us, okay. From table number 9 onwards, tables are more important for our syllabus point of view. Yeah. Here you can see the table number 9 is there. Just a minute. Yeah. Table number 9 is here, which gives the tension in the circular ring or wall, fixed base, free top and subjected to triangular load. Okay, we know that in case of water tanks, the water tanks will be subjected to triangular load like this. Okay, this is your, if water tank wall is like this, the pressure developed due to your water in the water tank, that will be triangular. So for that particular type of water tank which is having fixed base, these some coefficients are given here, and the value of hoop tension can be calculated by this particular formula. Okay, this particular formula is given in kg per meter. You have to keep in mind this particular formula is given in kg per meter. Kg per meter, we have to convert this into kilonewton meter. So this particular hoop tension is given by T is equal to double F coefficient multiplied by gamma HD divided by 2, gamma HD divided by 2. So this formula will become, this particular formula will become like this: coefficient multiplied by gamma HD by 2. Okay, so hoop tension is calculated by this particular formula. Okay, T is equal to coefficient multiplied by gamma HD by 2. Okay, so instead of this particular table, some tables is given in book also. Okay, I have taken that particular table in this particular presentation. Okay, because the table which are given in the book, that are in kilonewton per meter height. Okay, so we'll use this particular formula. Okay, first we will consider the hoop tension. So the formula which is used for calculating the hoop tension by using design table is this, that is T hoop tension, this is equal to coefficient multiplied by gamma HD by 2. Okay, now how we have to calculate this particular coefficient? Because we know the value of gamma, we will calculate value of H and D. Okay, H depending upon our requirement, depth of water. D is the diameter. Depending upon storage requirement, we can fix the diameter of water tank. And how we have to determine the value of this coefficient? Okay, that we can calculate, or that we can fix by using these tables. Okay, these tables are given in IS 3370. These tables are given in IS 3370 1967 part 4. Okay, only the problem is that the table given in the IS 3370 part 4, that are given in kg per meter unit, but we want it in kilonewton per meter unit. So these values are given in book, in any standard books these are given, and we can use these particular values. Okay, now for calculating the coefficient values are given here, okay, and we have to calculate the value of coefficient. For calculating the value of coefficient, what we have to do, we have to first calculate the value of h square divided by d into t. H square divided by d into t. You can see here this value is given here, that is h square divided by d into t. We have to first calculate this value, where capital H, this is the height of water in the water tank, d is the diameter of water tank, and small t, this small t is the thickness of wall of your water tank. Okay, this thickness can be fixed by using this thumb rule. T thickness is equal to 30 into h plus 50, 30 into h plus 50, where h is the height of your water in the water tank in meter. This value h is in meter. Let us consider we have this h as 4 meter, then this thickness will be 30 into 4 plus 50. So this will be equal to 170 mm. Okay, so this is how we have to fix the thickness. This is only a thumb rule. Okay, this can also fail while designing, but for getting certain value of thickness of water wall of water tank, we'll be using this particular formula. So for calculating the value of your for determining the value of your coefficient for calculation of your hoop tension. Okay, hoop tension you can see here is given by this particular formula. We can get these values. Okay, but coefficient is required to be determined, so that coefficient can be determined by using this particular table. This is given in IS 3370. So for calculating the value of coefficient, first determine the value of this h square divided by 2, h square divided by dt, and based on the value of h square upon dt, what we'll be doing, let us consider our h square upon dt is here 8. Let us consider this value, h square upon dt is equal to 8.0. Okay, then what we'll be doing, we'll find out the maximum value of coefficient. You can see here the maximum value of coefficient is this much, that is 0.575. 0.575 is the maximum value of coefficient for 8 value of h square upon dt. Okay, then we'll be using this particular value of coefficient. This particular value of coefficient is 0.575 for calculation of hoop tension. We'll use this value in this particular formula. Just keep this value of coefficient here, you will get the value of hoop tension. Okay, So this is how we will be calculating the or determining the value of coefficient for hoop tension. Okay, again you have to keep in mind the value positive sign indicates tension. Here the positive sign indicates tension. Okay, this positive sign here indicates tension. Okay, this point you have to keep in mind, and gamma is the density of whatever liquid we are retaining. Then for calculation of bending moment, okay, the bending moment will be more predominant up to a height of h by 3, or 1 meter or 1 meter. Okay, whichever greater. Okay, whichever is the greater. Okay, and bending moment is calculated by using this particular formula. M, bending moment, is equal to coefficient into gamma h cube. Okay, now the value of this coefficient are given in table number, just a minute, let me see, are given in table number, I think it is 10. Okay, in table number 10, in table number 10 of IS 3370 part 4. Okay, again you can see here these values are given in kg meter per meter. These values or these moment formula, bending moment formula, is given in kg meter per meter, and we want it in kilonewton meter per meter. We want this formula in kilonewton per meter. So this formula can be written in kilonewton per meter like this. M is equal to coefficient, okay, coefficient multiplied by gamma h cube. It is in kilonewton meter per meter. Okay, so we can use this particular formula instead of this particular formula. Okay, you can get this formula in kilonewton meter per meter in any standard book. Okay, or you can use the table which I will be providing. Okay, this is the table which will be used for calculating the moment. So formula for calculating the bending moment is M is equal to coefficient into gamma h cube, and coefficient can be calculated or determined by using this particular table. Okay, this is very simple. Okay, this is very simple. You can get the value of coefficient by using this particular table. What you have to do, you have to just calculate the value of this h square upon dt. H square upon dt, where h is the total height of water in the water tank, d is the diameter, and t is the thickness of your water tank wall. Oh, okay, let us consider we have got the value of h square upon dt as 8. We got the value of h square upon dt as 8. Then find the maximum value of your coefficient in this particular line. Okay, here you can see the maximum value of coefficient here is 0.38. Okay, we can see here the maximum value of coefficient is 0.38. So we will be using this particular coefficient value, 0.38 value, for calculating the bending moment, and just keep this value of coefficient in this particular formula of M is equal to coefficient into gamma into h cube, and you will get the value of bending moment. One thing you have to keep in mind, that the positive sign in this particular table, this indicate the tension is on outside. Okay, if this is the wall of your water tank, okay, if these are your walls of water tank, then the tension is developing on the outside here. Okay, outside here, this indicates the positive value. It indicates the positive value. So if we have positive value, the tension is developing on the outer side. Okay, you can see here this value of coefficient is up to a height of 0.7 h. Okay, similarly you will get corresponding value. Okay, okay, this table number, I think it is table number 12 in IS 3370 part 4, table number 12 IS 3370 part 4. Okay, this is the table which can be used for calculation of your shear at the base of your water tank wall. Okay, if the loading is triangular load and fixed base is there, we can use these values. what you have to do, you have to just calculate the value of h square upon dt, and based on the corresponding value of h square upon dt you can get the coefficient and calculate the shear force by using this particular formula, that is shear force is equal to coefficient into gamma h square, shear coefficient c into gamma h square. Okay, this formula can be used for calculating the shear at the base. Okay, then if we have hinged base, this is not required. Okay, but if we have the hinged base and the loading is triangular or rectangular, then we have to use this column. Okay. Okay. Should